Hi, my name is Jags Ramnaran. I'm the CTO at SnappyData. So SnappyData by definition is a Spark-based open source platform for unified analytics. So one of the primary use cases that you can create what we're calling as virtual warehouses on any cloud. So before I get to describing what SnappyData really is, let's first ask this question we get asked often, which is, why does it matter with so many tools in the marketplace already for analytics? So let's start by describing a set of requirements and a set of problems we want to solve, right? So the first thing is that when it comes to analytics, we really want new analytic applications on the cloud with a lot less complexity and a lot less friction than we see today. We also want an architecture that can leverage essentially a lot of the existing assets, especially databases like operational databases that already exist in the enterprise. And a lot of the data, frankly, is stuck in silos. How can we leverage that siloed data, a lot of the emerging data in these emerging sort of operational databases? And we also want to consume new streams of data that potentially is emerging through new applications in the cloud. And finally, we want to make sure that we can offer very high performance for interactive analytics, essentially be able to use a range of applications, right from self-service BI tools, microservices, and even real-time dashboards. Now, well, it turns out that cloud analytics is not all that simple. So take this graphic that you see on the right. It essentially depicts, if you may, a typical pipeline for how data is prepared for analytics, where the data is emerging in silos and operational databases. You essentially go through an expensive batch ETL process today, which moves the data from these operational stores into a warehouse. Typically, it's denormalized into cubes so that when it comes to interactive analytics, you get essentially higher performance. Likewise, we also see a range of new applications that are dumping data into these NoSQL-like stores, and from that stores again you are doing ETL to a traditional warehouse, which is even more complex given that the data is no longer flat. Finally, extract the data into files, and then you'll end up pumping the data into cloud storage, say S3, and that's where there's a big challenge, right? Because it so happens that even if you have 100 megabits per second connection, which is sustained, a terabyte of data transfer would take anywhere from 28 to 48 hours, let alone you're not running into, essentially, you have to assume that you won't run into problems. So what we see is folks quite often resort to specialized devices like the AWS Snowball, which you can essentially get to plug it into a network, copy your data into that device, and then ship that device. Or even land up using, for very large data sets, land up using the AWS trucking service, which is, again, all this is very expensive, very intrusive, right? On top of this, what happens if the data that is you've shipped is in fact changing, which is in fact the case if your really data is coming from operation stores, which implies that you have to repeat this process over and over again. What it amounts to is that if you are really trying to get all this data into the cloud, it is rather complex and the cost is rather very high. Now, what happens once the data is in the cloud? Well, it turns out even once it's in the cloud, it is rather very complex. So here is a processing architecture in the cloud, which is it's become a de facto standard. It's called as a Lambda architecture, and it is in fact from the AWS website. It's an example for a news aggregation service. I won't go through into all the details, but suffices to say that the architecture is rather complex. The data is ingested in batch into S3. The real-time data is ingested into some other real-time store, like in this case DynamoDB. And finally, for interactive analytics, the data is emerging through multiple databases: a relational reporting database, Presto for interactive analytics, and of course DynamoDB, which is a key value store. And it is an application that has to now stitch all this data together, let's say doing a join, let's say doing a correlation. All this is very unnecessarily complex. And of course, let alone time consuming, because you really have to master all these products in some sense, right? So what we're really proposing is that we're introducing, essentially, think about it as a layer that sits between your data sources and your cloud analytical applications, right? what we're calling as an in-memory driven virtual warehouse, which you can spin up or spin down on any cloud very easily, and which can dynamically expand or contract, right? It essentially discovers, catalogs, and caches hot data on the cloud local nodes. But the most important thing is that you can essentially federate your queries, your analytical queries, on data that's residing in main memory, data that could be literally be in your in your original data sources itself. In other words, the queries are analyzed and the right portions of the queries are directly shipped to your data stores, and we can do a federated query across your data sources and data that's sitting in main memory. And the primary idea is that for most of the data that you need for analytics, you essentially land up running those queries primarily in main memory, and it is significantly faster. Now, one way to think about this is like a new cloud cache that is purpose built for analytics. Like, for instance, you might be used to Redis or an Elastic cache for highly concurrent, let's say, key-based lookups, transactional applications. But think about Snappy as something equivalent as a caching tier, but is primarily designed for analytics, which basically means your input is ad hoc queries, and your data is very large, and the data comes from many different classes of data sources, right? It primarily runs in main memory, so you often don't have to do all this laborious ETL. You don't have to generate cubes. It's so fast that you can just dump your raw data and run your queries really, really fast. So in some sense, this is kind of what we think about as a virtual warehouse, and it can run, in fact, on any cloud. I would also say that you shouldn't be confusing this to a product like Snowflake, where the data is all on S3, and it isn't really meant to work directly with your operational stores, right? With SnappyData, you can keep your data on S3, you can retain it inside your operational NoSQL, SQL store, or even HDFS, and we would land up dynamically pulling the data into caches, perhaps even one sort of cluster per application if you want. Much easier to get this going. We will show you through a demo, right? So how does it really work? Here is a very, very simple depiction. You start a cluster which essentially launches an in-memory store inside of Spark. We parallelly connect from the cloud to any data source, which could be S3 or of course to your on-prem data sources, and we can draw out the schema. We can infer schemas automatically. We can register that into our catalog, and then we dynamically pull the right data sets into distributed main memory. And of course, we can even retain the data in S3, for instance, that we pulled in. And the most important thing here is that, hey, you can literally retain the data in raw form. Of course, you might be enriching it, but the point here is that you don't have to really generate cubes and aggregations, go through a complex pipeline, use Lambda or even BI extracts, because the data can be served at pretty amazing speeds. And finally, the important point also is that if the data does in fact change in an operational stores, you can rely on change data capture mechanisms, so that as the data changes, they can be pumped directly into the cloud. And we deliver this multi-cloud strategy through Kubernetes. We'll get into it as we demo it. And the applications now interact with SnappyData using a range of APIs. The Spark Java Scala APIs. We support SQL through JDBC and ODBC. And of course, you can also use REST to come in and essentially interact with the system. Here's a pretty high-level view into a bit more of the architecture. One way to think about how we have implemented this is to look at it as if it's like Spark++. At the shell all looks like Spark. What I mean by that is you land up using Spark SQL. You can use essentially any of the Spark APIs, the streaming, the graph, the MapReduce, the ML APIs in Spark, and then for connectivity to all sorts of data sources, we again rely on Spark connectors, right? And almost every modern data source has made sure that the latest version of the products are all enabled through Spark. And the guts of Spark is where we bring in a lot of the meat, right? We have our own in-memory database that's highly concurrent, provides much significant higher performance. We're introducing essentially the first generation of what's called as approximate query processing. And of course, it's also capable of running transactions. Okay, now it's time for me to get into a demo. I essentially break it up into two parts. Part one, which is what I'll cover here. We'll look at essentially interactive analytics. using notebooks and BI. See how easy it is and how fast it is compared to alternatives. And part two, which is a separate screencast, we'll look at real-time analytics. Essentially, we will look at capturing events inside the operational database. In this case, it will be MongoDB. And we'll route those events to SnappyData through a streaming pipeline. So essentially, the idea is that, hey, can I essentially get my insight if I'm using a BI tool or any other tool? My insight and my analytics is always on the freshest data. All right. So what do I cover in part one? So here it is. So the first thing is that we will show you, I'll show you the cluster and services running on Kubernetes. I mean, Kubernetes is our answer for how we essentially achieve multi-cloud. Everything is done using a couple of Kubernetes operators. I'm not going to get into Kubernetes, but I will essentially show you the commands I use, and we look at the Kubernetes dashboard. Then we will get into a notebook environment where we will immediately connect to data sources, where we'll show you how easy it is to infer schemas. We look at transformations. We literally, through a sequence of clicks, we will essentially load our data into our cloud cache, in this case SnappyData. Then I use Zeppelin to explore data using ad hoc SQL. We'll compare that to Spark performance using Parquet as a format, which is the fastest way to run Spark analytics. Then we'll look at, say, hey, given that SnappyData exposes everything also as data frames, how easy it is to use Spark's libraries to featureize and generate machine learning models. And then we'll come back and look at this very interesting topic, which I covered in my previous screencast. Essentially the use of stratified samples. So let's say the volume is very, very large and I cannot afford the resources, in this case memory. The idea would be to generate one or more stratified samples which are deeply integrated into our query processor, and how the stratified samples helps you to not only take large data sets and condense it into something very, very small. At the same time, you can essentially get analytical speed answers for the questions you could ask. And finally, we will look into a small illustration of using a BI tool to visualize our analytics. In this case, we will use Spotfire. All right, so here's the demo architecture. Everything is running on Kubernetes. First thing is that we use a data set. In this case, I'm using the airline on-time performance data that's published by the FAA. We have about, I believe, 7 years worth of data amounting to about 210 million on-time performance records for all airlines and all flights. So that data has been loaded into S3 in Parquet format. So we essentially point to that data, we infer the schema, register it as virtual tables in Snappy, and of course cache it in Snappy. Then we also get some additional data from MongoDB. In this case, we essentially get airline reference data from MongoDB. Then, as I mentioned before, we will run one or more notebooks to do simple analytics, essentially analytical queries on this data set. And finally, we will show you the use of Spotfire. All right. So with that, let us look at this is the Kubernetes shell. So I've already launched a Kubernetes cluster on the Google Cloud Platform, the GKE. Of course, we also support other Kubernetes environments. Specifically, for instance, we support the Pivotal Container Service. And the benefit of using something like Pivotal is that you could essentially run Kubernetes on-prem using VMware virtual machines. And you get essentially you're running our operators in Kubernetes, and you can essentially take that same operator, switch over to Google Cloud and run it, and you'll get the exact same consistent a consistent feel for how your applications, in this case SnappyData and the entire analytics framework we are running, will be very consistent across all these sort of cloud environments. That's the idea. So how did I launch my clusters, my Spark components as well as my SnappyData components? We essentially use a Helm-based operator. Just through a single command, we have all sorts of sensible defaults, and you can override some of the defaults here. It's very simple, so you don't have to really know a lot of the details around Kubernetes objects and resources. So the Helm LS gives me the real components that I've deployed into Kubernetes. As you can see, I have deployed a Cassandra cluster, a MongoDB cluster, and a SnappyData cluster. So let's look at the dashboard real quickly. So here is the Kubernetes dashboard. And what you can see here is that if I click on the clusters, I have a single cluster running. I'm just a very small cluster. I'm only running a cluster of size 4. Each node has about 4 CPUs for a total of 16 CPUs. And within that small cluster, I'm running and exposing all these services. I have Cassandra, Mongo, I have the SnappyData cluster, and several endpoints of SnappyData exposed. And finally I have Zeppelin, which is our notebook server that I've exposed. I've also exposed Jupyter in case you want to essentially run Python workloads. The workloads here is nothing but the set of containers. I mean, without really getting into Kubernetes details, these are the pods that are running. A pod is nothing but an encapsulation on top of a Docker container. So for instance, if you look at the SnappyData server cluster, which is really nothing but the SnappyData data servers, I have 3 of those guys running. And of course, at any one point in time, you can, if you want, scale and rebalance the data across more nodes if you want to, right? So now let's look at the SnappyData dashboard. Here's the SnappyData dashboard, and it shows you that we have 3 data servers and located on lead node that's running. And I've also connected to our Zeppelin server environment. So here is the Zeppelin server environment. Let's first look at setting up our data sources. In this case, like I pointed out, the first thing is that I want to make sure I can connect to my Mongo server and really get the data from Mongo and cache it in. So it's a fairly straightforward self-service kind of notebook here. The first step is you register a data set, give it a name. I'm pointing to the MongoDB database. Here's the URI, and I'm specifically pointing to a specific collection. And the sample size really allows us to say, hey, if I run this, go and look at 1,000 random samples inside your MongoDB database, and then infer the schema automatically. So let's just give it a go. So as you can see, it connected to Mongo. And it resulted in creation of an external table in SnappyData called airline ref, and it's printed out this nested schema, which is what MongoDB has inside this collection. Of course, you can take a look at that sample data now, given that it's a table, and you can see that. Of course, you can do arbitrary transformations, and then finally, let's take that external table and cache that data inside a SnappyData row table. In this case, this is really a small table. It's got 1595 records. So we got our first table registered, essentially pointing to MongoDB. Let's go back. The next thing I want to do is to make sure I can essentially get access to the larger data set, which is sitting on S3, right? So again, you can, we support S3, HDFS, GCS, and a variety of file formats by which you can essentially upload your data into Snappy or register. So it's the process is exactly the same. You define a data set, you select the data source, you select the format in which the data exists. Then, if depending on the source and the format we've selected, that will automatically result in you providing, we're showing you additional options. In this case, if I'm connecting to S3, obviously I need my S3 credentials and the S3 bucket from which I'm going to fetch it. I'm not going to run this here because it does take a while to load 210 million records from S3. So I've already loaded the data. This table has been again registered. Like I said before, with Mongo, we infer the schema and we register into our catalog as an external table. And likewise, I've essentially cached the data into a column table in SnappyData. One interesting thing I want to point out is, of course, you might say, hey, my tables that are there in the source versus what I want to see in my catalog might be different. In other words, you might want to enrich, you might want to pivot, you might want to generate cubes, you might want to add additional columns. So here's a very simple example, just using this Spark API, how you can do that. Right? All that is relevant here is you can essentially access any SnappyData table, an external table or a cache table, as a data frame in Snappy. Here it's called df. Of course, I'm using Scala, so the types are inferred here. And I can use the Spark API. So in this case, I'm adding an additional column to this data frame called ID, and I'm essentially using a built-in function that gives me monotonically increasing number. Then, of course, I can turn around and simply save that data frame as a table. Okay, so I'm not doing it right now, but so you get the idea. So if you look at now our dashboard, you'll see those two tables. So you see that the cached tables are available inside Snappy, and the catalog has these external tables that are pointing directly either to S3 or MongoDB registered here. And as you can see, the airline cache table has got 210 million records and consumes about 12 gigabytes of memory. Of course, our cluster is really small. All right, so let's go back and see if we can run some simple analytics on this data set. So let's go through a little exploratory example to run some analytical queries. So as you can see here, what I have is all the panes or the paragraphs that you see on the left are really running directly, are pointing to directly the Spark data source, in this case the Spark Parquet files. And on the right hand side, I'm running the exact same queries pointing now to the cached tables. So no difference, the schema is exactly the same. One comes out of memory, one is essentially directly going against the source. So if you look at the first query, where I'm saying, hey, let's find out which airlines have had the most flights. So I'm essentially doing a count query, and I'm joining the airline with the airline reference table, and I'm grouping by essentially the airline name, and I'm picking the top 8 of those airlines. I'm not going to run this thing because, as you can see here, it took over a minute. So if you run the exact same query using Snappy, that should take less than a second, right? So it took about a second. We can go in here into our dashboard, and we should be able to see that this is the query I ran, and it took about 0.9 seconds to run that query. So of course, you can run additional queries. So the point being that if you are using essentially SnappyData versus Spark, you should see anywhere from 10x, 15x, in some cases even literally 100x improvement in your performance, in your speed. So you make a decision to say like, hey, which classes of data is most frequently essentially accessed from either my BI tool or is relevant for my applications, and you can decide to cache it and leave the rest as external tables. Okay. All right. So that's the access. We demonstrated a very simple sort of exploratory notebook. Now let's look at what if I wanted to essentially land up doing machine learning models. So I'm not going to go through the details here. Let's just skim through it. Here's a notebook that is essentially saying, hey, can I essentially build out a model to predict arrival delays for my airlines based on the data set that I already have, right? So I mean, here are some paragraphs where these are just nothing but Spark API and code. The beautiful thing is that Spark is fused into SnappyData, which means you can create a notebook and use any of the Spark APIs, machine learning, graph APIs, of course, MapReduce APIs, all the rich transformation APIs, and all that sort of stuff. So any table is also accessible as a data frame, as I said. So here is a thing that says, hey, give me the statistics of the various columns. I can look at correlations between departure delay and arrival delay. So essentially, I'm exploring, understanding my data sets, and then finally I can turn around and featureize. So in this case, to featureize, we explicitly first create a sample of my data set. And then I use a variety of techniques to featureize, and we essentially land up using a decision tree as the as our algorithm to really predict sort of arrival delays. Okay, so that's a little notebook on using machine learning. I just want to touch on this additional thing which we talked about, which is approximate query processing, or the use of sampling technology. Like I said before, if your data set tends to be very large, let's say, in this case, our data set is relatively small, it's got 210 million records. What happens if the data set was billions and billions of records, and you really can't afford that memory? You don't want to pay that price of memory or the compute resources for a virtual database, virtual warehouse in this case. So what you can do is you can simply create sample tables. So think about sample tables as if they're like indexes on the data set that might be sitting at the source. So in this case, I'm creating, it's a simple set of extensions we have on top of SQL. Of course, we have a data frame API also. So you create a sample table. In this case, I'm essentially stratifying it on on these 3 columns, and I'm saying give me a sample that's just 1% of the full data set. And we supply access to the full data set simply using a subquery in this case, where I'm saying, hey, select these columns from airline, and as you noted probably before, airline is simply an external table pointing to a Parquet data source. And lo and behold, as you can see here, if I run start running my queries, what you'd see is that the query looks exactly like the query on the left, which is going after the full data set or the exact data set. The only difference on the right is that we have this with error clause. That is a signal to our engine to say, hey, if you have the relevant samples available, figure out which sample you can use. But the key restriction here that the user is placing is that he's saying, give me an answer back from the sample as long as the answer is at least 90% correct. So in other words, this with error of 0.1 says I can tolerate a 10% error. Of course, in this case, this query is giving you literally 100% correct answer, essentially saying that, hey, the row count is 210 million, even though the real count inside the sample is just 2 million records. So it's a beautiful way to, or a very smart way to really build out high performance analytical applications, especially the ones where you are visualizing your answers, your aggregations. Because as you can see here, even though the answer may not be 100% correct, visually you can never tell the difference. I mean, if you're looking for a pattern, this is a great way to essentially use synopsis. So here is another analytical query which we ran before, where I'm essentially finding out which are the airlines that have the most flights, right? Likewise, you'll see many queries I'm running where here it's taking 20 seconds instead of 1 second with the sample, all right? All right, so finally then, let me switch to saying, hey, I showed you the use of notebooks for exploratory analytics. We looked at how easy it was to set up access to my data sets that are external. Finally, let's look at whether I can get visualization using a BI tool. So in this case, I'm using TIBCO Spotfire. You could use Spotfire, you could use Click, you could use Tableau. Any visualization tool that can speak JDBC or ODBC should absolutely work just fine. So I'm running TIBCO Spotfire and using a Microsoft Remote Desktop. Spotfire is actually also running. In fact, right now Spotfire is running on the AWS cloud. So I'm using the visual tool is called Spotfire Analyst, which is really what you use to visually sort of analyze what you want. So in this case, as you can see, I'm already connected to SnappyData and I have the airline cache table accessible now, which is the data set I'm using for analysis. And Spotfire automatically looks at all the columns and figures out which columns make up categories and which columns make up measures. And all I do is drag and drop to do my analytics. So let's actually take unique carrier. Let's say I want to do the same thing, which is I'm trying to find out the average delays for each airline. So all I do is drop 1 on this pane, then I pick up so as you can see, the moment you drop a column in here, it automatically runs a query where it's found out all the unique values for that column. So in this case, these are all the airline codes. So let's take arrival delay, plop it into this column here. We don't want a sum, we want the average arrival delay. So we switch over to average and voila. I mean, it's immediately running a query on the 210 million records and plotted the answers here. So of course we can go back and see if what Spotfire ran. In this case, as you can see, it ran a range of queries. This is the last query we ran, which is a group guy query, and ran in 0.5 seconds, right? So maybe you want to sort of say, hey, I want not just by unique carrier, but I want to see the results even by year. So now I'm grouping also by year. Again, it's a different query that's running, obviously difficult to interpret with so many answers are coming back. So maybe what I want to do is I want to add a filter and I can pick, let's say, United Airlines. And the moment you pick any of these things, again, it's running a query in the background, giving you the answers back. So there you go. I mean, so we covered what I wanted to show you. The fact that I can load from S3, I can work with Mongo. This is a small cluster running on Kubernetes. So you can essentially scale the cluster at any given point in time. If there are any failures, Kubernetes will automatically handle failures. I'm running Zeppelin, which is auto-connected to the SnappyData cluster. I didn't show you Jupyter, but you also have Jupyter as an option in case you want to run Python and work with the same tables. So now we'll go through part 2 of the demo. So in this part of the demo, we'll look at how to achieve interactive analytics where the data is in fact changing. So we use a technique called as CDC, or change data capture. For those of you who haven't heard this term before, this essentially refers to the technology that can capture transactions as they happen in databases, and it can route it to one or more endpoints. It's typically a use case for this would be to replicate databases essentially. Okay, so before we dive into this, let's actually revisit and refresh our memory on the problem we went through for demo 1. So like you know, all new data is often emerging to customer-facing apps and captured as transactions in operational databases. From there, you'll end up going through classic ETL to other analytical databases, applying transformations. And if you're going to operate in the cloud, the data has to be periodically copied back out to the cloud. So like I said before, this is a fairly expensive process, very time-consuming process. Often the data you're analyzing is stale, and so your insight essentially is also stale, right? So what we really want is to be able to capture changes as they happen and be able to route it to our analytical storage, right? So the most common choice today is to inject a message bus like Kafka into the application pipeline. And as you can see, I'll just talk through this. It's rather very difficult. So here is a typical streaming pipeline that you potentially see today. One example, I mean, there are many variations to this obvious architecture, right? As your application microservices, let's say, transacts with the database, say in this case, Amazon RDS, your application might also route events to Kafka. Then the Kafka messages would have to be decoded by either using Spark Streaming, Flink, or you can substitute your favorite stream processor. And then finally write it out to your analytics store. If you're operating in the cloud, maybe you're writing it to S3, formatted in Parquet, or maybe you're just writing it out to a traditional warehouse like, let's say, Redshift. Well, there are a number of challenges here, right? First, well, how exactly can we achieve consistency if we're going to write as transactions happen both to Kafka as well as to our database? To essentially achieve consistency, you have to worry about two-phase commits, you have to worry about various failure conditions. And moreover, what happens if you land up changing the schema in one? Well, you have to consistently land up changing the schema in other, else you again land up having potentially inconsistent data in our analytics store. And finally, you have to write code that has to decode data objects from Kafka. Maybe the data was formatted as JSON, and storing it with consistency to your analytical store, which is again your responsibility. So the other challenges have to do with when failures happen, you might land up having the messages delivered twice. On top of that, if the events land up being DML events like updates and deletes, is rather very complex. So instead, what we're really proposing is using a design where your application essentially only works with your operational store, and you use CDC technology to capture the changes in real time in a transactionally consistent manner, and just keep pushing the delta continuously to our essentially snappy hybrid store. So it's a rather much more simpler, far fewer sort of pieces that can break, and even if anything breaks, everything can recover fully in a consistent manner. So the way we essentially accomplished this in our cloud platform is by deeply integrating with an open source platform from Red Hat called Debezium. It's really designed with using Kafka Connect. You can go check out debezium.io for a full understanding of what it does. But we have landed up essentially deeply integrating. So as I'll show you, this requires no application coding other than simple Spark-based transformation. If your schema that you use for analytics lands up being different than what you have in an operation store. I won't be getting into details of how exactly all this works. But one important point to note is that the CDC engine uses Kafka Connect to tap all the committed transactions in let's say if you're using MySQL and sort of bin log, and that's what gets pumped to your destination. So essentially what is guaranteed is that you only see things that have in fact completely been committed in your transactional store, and you essentially land up maintaining source ordering, which is a big plus compared to, let's say, if you land up just using Kafka. All right, let's just revisit the demo architecture from before. In part one of the demo, we showed you how to load data from Mongo, static data from S3, infer schemas, run interactive analytic using notebooks, and also we showed you how to run analytics using a BI tool like Spot5. So we landed up using, you might recall, the airline on-time performance data, about 200 million records is what we landed up analyzing. In this case, we just introduced a few additional components. We use MySQL to simulate our transactional database that's being continuously being written into from a customer-facing application or microservices. And then we essentially run Debezium that's capturing these events and routing it to Snappy. All right, so let's take a brief closer look at what the demo is doing. We simulate an application by continuously writing records to a MySQL table called airline perf now that you see here on top. The transaction log, which is really bin logs in MySQL, are continuously watched by Debezium, and Debezium internally essentially is based on Kafka Connect. The events are then formatted into JSON and written out to topics in Kafka. But default, each table, if you sort of say, hey, here is a complete schema in MySQL you want to monitor, each table would have land up having its own one associated distinct topic in Kafka. Then inside SnappyData, we use a component which we call CDC ingester that continuously reads from Kafka, understands natively this Debezium formatted messages, transform these back out as rows, and writes it in a highly efficient parallelized manner to our target column table. Of course, the whole chain is protected from failures and guarantees that any writes that happen all the way are made idempotent. In other words, we guarantee consistency of all changes happening in MySQL and how those changes will emerge in column table. All right, so let's get right into our demo here. So first, let me show you guys my Kubernetes cluster. So as you can see, we went from a cluster of size 3 to size 4, a very small cluster. Here are all the workloads, essentially pods that I'm running. As you can see, I've started a couple of new pods. I'm running MySQL 5.6, in a single pod. We are also running Kafka, and Connect MySQL is really Kafka Connect running Debezium, which is in turn connecting connecting to MySQL, writing it out to Kafka. And you might recollect all the other Snappy services that we walked through in our previous demo. All right, so there are basically, when it comes down to the demo, there are really, once your infrastructure is set up, which basically means Kafka, Debezium, and SnappyData is running, all you really have to do is primarily essentially two things to stream our real-time events all the way into our analytics store. First, we configure our CDC connector to monitor MySQL, and the second is you configure the CDC ingester I talked about in SnappyData to stream our Kafka events and publish to our column store. So okay, so let's see how do we do both of these things. So once Debezium is running, you can essentially use a REST API, and this is the REST call that essentially says, hey, Debezium, I want you to monitor my MySQL database, use these credentials, here's a server, and the database whitelist essentially says, I want you to use the database called inventory, and essentially it's monitoring any tables that emerge or changes in inventory, and then it's going to route it to, in this case, a Kafka topic called, dbhistory.inventory. Okay. So I'm just trying to run it, but I actually already have started the Debezium connector, so it's already listening on that specific schema in MySQL. So that's as simple as setting up Debezium. We're already set up to kind of monitor any changes that are happening. So very quickly, let's take a look at how do we set up our stream ingester in SnappyData. As you might recall, SnappyData, this is a dashboard. I think I went over this before. We're running essentially 3 data servers in SnappyData, let's actually see if we can get our ingester working. So the CDC ingester is just set up as a notebook and it actually runs as a Spark structured streaming program inside of SnappyData. And here all you essentially tell us is the list of Kafka brokers, the Kafka topic you want to listen to, and then the target table that you want to ingest into. And for streaming, you need a checkpointing directory, so in case there are failures, we are able to make our entire streaming pipeline to be idempotent, right? So let's just run this paragraph. So it sets up our configuration. Then the very next thing we do is we start, and let's actually see if our ingester is running or stopped. So the print status tells us that the ingester is in fact stopped. We'll start the ingester, which will take a few seconds to get going. It's a fairly straightforward structured streaming program, and also lands up using the Snappy sync, so that it's making sure that anything that's coming to Kafka lands up inside our Snappy tables. So looks like our ingester is up and running. Let's make sure it is in fact running. So as you can see, it's waiting for our next trigger. All right, so the final step in our process is to literally go and write something out to our MySQL database. So let's just do that. All right, so let me connect to my MySQL pod using kubectl in Kubernetes. So I'm going to log into the MySQL shell, and I'm going to switch to this database. So if you go show tables, we should see a bunch of tables. So what I'm going to do to simulate continuous writes to our operational table, in this case, we are going to use this table called airline performance now. It's equivalent to saying that all the aircrafts are landing, we are essentially capturing its on-time performance, and those records are being continuously, we're simulating as if those records are continuously arriving to our MySQL database. So we're going to keep it simple, and what we're going to do is we're just going to simply write into our store by simply capturing a bunch of events in another table. So this is essentially simulating continuous writes. So that's what we'll end up doing. So we'll just say, hey, let's just continuously write into this table, and the idea needs to be to figure out whether these changes continuously land up arriving into our column table, right? So as you can see, this is the table. And as you can see, it's already started to grow. It's now up to 28,000 records. And if you go back to our ingester program, we can print the status again. As you can see, it's saying it's processing new data as it's arriving. All right. So finally, we have new data continuously arriving as it's arriving to MySQL into our column store, so it should be ready for analytics. So here is a very simple example where we essentially compare historical on-time performance. So essentially looking at arrival delay for large airlines, from our historical store. So we run that query, and then of course we can say, hey, this is the same, pretty much the same query, but just going on this airline performance now. So of course the records are building up. So obviously, as we run this, we might see different results as we keep running it. So as you can see, there is still no data for WN, which stands for Southwest Airlines. So if you keep running it over time, we will essentially see that data too. All right. So I guess I showed you how we set up Debezium, how easy it was to start Debezium monitoring MySQL. How did we route it into Kafka? From Kafka, how did we pick it up very easily just by running that ingester into SnappyData. So with that, let me just go back to my, let's just summarize real quickly what we did. So in part 1, we really went through showing you how easy it was to connect to any data source in parallel from S3, Mongo, any SQL database, and how we'll end up pulling up the right data sets into distributed memory. We showed you how easy it was, where we didn't really use any data pipelines, no ETL. We showed you how fast it was compared to Spark. And then finally, in this part of the demo, We showed you how easy it is to capture changes on any source database. In this case, Debisim actually supports about 5 databases today, and we are planning to add more to capture CDC changes, and we showed you how to route it into Snappy so that we can do real-time analytics. So with that, I encourage you to go check out our website. Of course, SnappyData as a project is an open source project, free to download. Try it out. Give us some feedback. Thank you very much.